Ladies and gentlemen, welcome to this particular video on the methods of solving system of linear equations using LU decomposition. In this particular video, we are going to discuss the Crout's method of decomposition, which is also one of the LU decomposition methods. Before I move to the specific topic of Crout's decomposition, let me remind you of the general concept of LU decomposition, or solving the system of linear equation using the LU decomposition. In my previous video, we realized that we are solving the system AX is equal to B. And the idea behind LU decomposition is to decompose the matrix A into a product of two matrices, L times U. And so we are solving LU X is equal to B. And in that means that to solve the system, we can assign our UX to be a vector of the same size or length as X. And then we solve the Ly is equal to B. We realize that at this stage, we would know the matrix L and know the vector B. And for that matter, we can find the entries of Y. And when we get the entries of Y, we will move in straight to this particular system to solve for our X, which is the main focus. So UX is equal to Y, where we will get the values or the entries of the vector X that we are looking for from the main problem or the main system. So this is basically the general concept. And we're learning how to decompose the matrix A into a product of two matrices, lower triangular and upper triangular. We discussed the Doolittle method in my previous video. And today, I'm going to take you through the second method, which is the Crout's decomposition. And so let's move in straight and continue by looking at the Crout's decomposition. From the left side of your screen, you can see the general form of the Crout's decomposition. And as usual, I'm going to use a smaller matrix, a 3x3 matrix, which looks like this: A11, A12, A13, then A21, A22, A23, A31, A32, and A33. This is my matrix, and I want to decompose it into the Crout's way of decomposition. And the lower triangular, let me use different notation here: L1, 0, 0, L2, L3, 0, L4, L5, and L6. So you see this is a lower triangular matrix multiplying an upper triangular matrix, this time Z1, and then we have U1, U2, 0, 1, U3, 0, 0, 1. So that is the Crout's way of decomposition. So you see that the upper triangular has a special shape such that the main diagonal are all 1, 1, 1. And then above the main diagonal gives the entries, which are some zeros and other entries. But below the diagonal are strictly 0. In the same way, the lower triangular has the shape of 6 entries below the zeros, or from the main diagonal down. So this is the Crout decomposition. So just as we did in the previous method, we will just go by the idea of matrix equality and multiply the right side of the equation and compare entries to find the values of L1, L2 up to L6 and U1, U2, and U3. So multiplying the right-hand side of the equations of that particular equation, we have row 1 multiplying column 1 will leave us with R1, L1. So row 1 multiplying column 1 or row 1 times column 1 will give us L1. Then row 1 times column 2 will give us L1 U1. Row 1 times column 3 will leave us with L1 U2. Then row 2 is the turn of row 2, column 1 will give us L2 here. Row 2, column 2 will give us L2 U1 plus L3. Then row 2, column 3 will give us L2 U2 plus L3 U3. And then we go to row 3, and using row 3, we're going to have the entries come out as, so using row 3, we're going to have the entries come out as row 3 times column 1, L4, row 3 times column 2, we get L4 U1 plus L5, and then row 3 times column 3 will give us L4 U2 plus L5 U3 plus L6. So this is our product of the two matrices on the right. So now, just as in the previous case, the L1 over here, the L1 will be equated to A11, L2 will be equated to A21, and then L4 will be equated to A31. So these are the entries I usually call we'll be having for free. Then we move according to sizes and come to L1, U1, the second entry on row 1, and equate it to A12. Then L1, U2 will be equated to A13. Then we come to the entries, the second entry on row 2, and equate that one to A22. Then the second entry on row 3, we equate that one to A32. Then we move to the third entry on row 2 and equate it to A23. And finally, the third entry on row 3 and equate it to A33. So this is what we're going to do to get the entries L1, L2, L3, L4, L5, and L6, as well as U1, U2, and U3. So basically, this is the decomposition for the first approach of the Crout method. So let me pick the same example that we solved under the previous method and try to solve using the same system, this approach, and see if we're going to get the same set of answers. So from the problem on the screen, we can put it in the matrix form as 3, 5, 2, 0, 8, 2, 6, 2, 8 times x1, x2, x3 is equal to 8 minus 7 26. So this is the system in matrix form. So we are going to take out the matrix A, which is this one, the whole of the matrix A, and decompose it into the lower triangular times an upper triangular. So in this case, I'm going to have my A matrix come out as 3, 5, 2, 0, 8, 2, then 6, 2, 8. This is equal to L1, 0, 0, L2, L3, 0, L4, L5, L6 times 1, U1, U2, 0, 1, U3, 0, 0, 1, like this. So when we do the multiplication, as we saw earlier, we're going to have it come out as L1, L1, U1, then L1, U2, then L2, L2, U1, plus L3, then L2, U2, plus L3, U3, and finally we have the row L4, we have the row L4, L4, U1, plus L5, then L4, U2, plus L5, U3, plus L6. And that is the product of the right-hand side. So now we equate or assign corresponding entries, and then we say that L1 is equal to 3, L2, because this one is equal to that one, and this is equal to that. So L2 is equal to 0, and then L4 is also gotten for free. We get L4 for free, and it's equal to 6. So we have this. Then we come to the second entry on row 1 and equate it to 5. So we have L1, U1 is equal to 5, but we know L1 to be 3. So that implies that U1 is equal to 5 on 3. Easy. Then L1, U2 is equal to 2. According to the entry there, we are here, and I'm picking this particular entry, is equal to 2. And that implies we know L1 to be 3. So straight away, our U2 is equal to 2 on 3. Then we move to the second entry on row 2, which gives us L2, U1 plus L3, and that is equal to the second entry there has a value of what's 8. So that is 8. Some substitutions to be made. L2 is 0. So fortunately, the whole of this will go to 0. And so it implies that our L3 is equal to 8. Then we go to the next entry over here. We go to this place, and we're going to have it as L4, U1 plus L5 is equal to, what is the entry there? That one is 2. So here we have the value for L4 to be 6. We have U1 to be 5 on 3. So we have 6 into 5 on 3. 6 into 5 on 3. Then plus L5 is equal to 2. So clearly this particular 3, this 3 will cancel the 6 2 times and multiply by 5 gives us 10. You take the 10 there and we can straightforward say that our L5 is equal to -8. Then we move to the third entry on the second row and write it as L2 U2 plus L3 U3, and that is equal to the number 2. We are talking about this entry here, and it's equal to the number 2. So this is equal to 2. And what do we have? We have L2 to be 0. Fortunately, this is 0. Then we have L3 to be 8. So it means we have 8 of times U3 is equal to 2. And that implies that our U3 is equal to 2 on 8, which is 1 on 4. And finally, we write L4 U2 plus L5 U3 plus L6 is equal to the entry there. This time it's this entry, which is 8. So we put our 8 there. Then what are the substitutions? L4 is 6. U2 is 2 on 3 plus L5 is -8 and U3 is 1 on 4 plus L6 is equal to 8. So solving this will give us, this times that will give us 4 here minus -2 here, -2, and plus L6 is equal to 8. And simplifying that, this gives us 2. Take the 2 there. Simplifying that gives us our L6 to be equal to +6. Our L6 is +6. And that is what we have. So now we can look at these values and write all our lower triangular matrix and the upper triangular matrix. So what is the lower triangular matrix? L is going to give us L1. We know for the entries L1, L2, L4, we're just taking for free as, so we have 3 here, 0, 0. Then L2 came out as 0. L3 came out as 8. That is this. Then we have a 0 here. L4 was also one of the values we took for free. It came out as 6. And then L5 came out as -8, as you can see over there. And then L6 came out as +6, as here. Then our U is given by, of course, we know there is 1 here. U1, we got the value of U1 as 5 on 3. 5 on 3. U2 came out as 2 on 3. And then 0 here, 1. U3 came out as 1 on 4. 0, 0, 1, and this is our U. So these are the entries, U3. Remember, we computed it over here, and it's that. So now that we have the decomposed matrix, or the lower triangular and the upper triangular, we go straight to solve the system, where we said that we are solving AX is equal to B. A is now equal to L times U, and so we have LUX is equal to B. So we set UX to be equal to a certain Y and solve our LY. We solve LY is equal to B. And so we are going to have L, which is going to give us 300,080,6 minus 86 times Y. Y must be of the same size as X. So Y1, Y2, Y3, and it's equal to our B. The B is 8 minus 7, 26. So straight away, this is a lower triangular system, a system of coefficient matrix, which is a lower triangular, which can be written as 3y1 row 1 times that is equal to 8. Then row 2 gives us 8y2 is equal to minus 7. Then row 3, 6y1 minus 8y2, then plus 6y3 is equal to 26. So this is the system we have to solve. So straight away, we can say that our y1 is actually equal to 8 on 3. And then y2 is equal to minus 7 on 8. That is very easy. Then we substitute all that into equation. The third equation, which gives us 6 into y1, 8 on 3, minus 8 into negative 7 on 8, plus 6y3 is equal to 26. Now this gives us 3 goes into 6 2 times, and 2 times 8 gives us 16. Then plus 7, then plus 6y3 is equal to 26. So this gives us 23. Let the 23 go there. We'll be left with 3 there. And so we have 6y3 is equal to 3, which implies our y3 is equal to 1 over 2. So we can write the vector for y as y1 is 8 on 3, y2 is minus 7 on 8, and y3 is 1 on 2. So this is our vector y. And so now we can go ahead and solve the system that contains our x. So ux is equal to y. And what is our u? Our u from the previous, from the calculations up there, is like 300,080, then 6 minus 8, 6. And this is our u from, as we got it from here. Oh, sorry, this is the L. So I just have to write the u, and the u So the U is taken from that as this 1, 5 on 3, 2 on 3, then 0, 1, 1 on 4, then 0, 0, 1. This is our U multiplying x1, x2, x3, and that gives us our Y, which is 8 on 3 minus 7 on 8, and then 1 on 2. So this is what we have. So clearly, this is going to give us a system that will be easy to solve. So we have x1 plus 5 on 3 x2 plus 2 on 3 x3 is equal to 8 on 3. Then we have x2 plus 1 on 4 x3 is equal to minus 7 on 8. And then finally, the last equation is x3 is equal to 1 on 2. So straight up, we have our x3 is equal to 1 over 2. Substituting that into the second equation gives us x2 plus 1 on 4 into 1 on 2 is equal to minus 7 on 8. And that will give us x2 is equal to minus 7 on 8 minus 1 on 8, which gives us negative 8 on 8, which is negative 1. And finally, we substitute those two entries or those two values into equation 1, x1 plus 5 on 3 into x2. x2 is minus 1, then plus 2 over 3 into times x3, which is 1 over 2, and that is equal to 8 on 3. So what do we get from here? If you simplify, we are going to get x1 plus or minus 5 on 3 plus 1 on 3 is equal to 8 on 3. So I can carry everything out there and get x1 is equal to 8 on 3 plus 5 on 3 minus 1 on 3. And that's 8 plus 5, 13 minus 1 gives me 12 on 3, which is 4. So as in the previous solution of the same problem, our x vector is coming out as x1 is x1, x2, x3 is coming out as x1 is 4, x2 is minus 1, and then x3 is 1 over 2. And this answer is the same as what we got using the previous decomposition method. And that is the first approach of the Crout decomposition. So this gives us the first solution of the first approach of the Crout decomposition. To just recap some of the few steps, you write the matrix in the decomposed form. We're using the Crout decomposition as L1, 0, 0, L2, L3, 0, and then L4, L5, L6. You can use any other variable notation you want. Then we have 1, 1, 1 on the main diagonal. That is very, very important. You need to know how the Crout decomposition is written. This one is 1, 1, 1 on the main diagonal. U1, U2, U3 can be denoted by any other variable. Then you multiply the right-hand side and get your new matrix on the right. Then you just assign corresponding terms or equate corresponding terms to get the final solution of this particular system. So that is the Crout's decomposition, and it gives us the same answer as the Doolittle. Let's, those who are interested in Gaussian elimination approach of the decomposition methods, let us look at how we can find a smart second approach to the Crout's decomposition. Approach 2, as you see on the left side of your screen, called method 2, you use the 3 steps in Doolittle method 2 or Doolittle approach 2 to find UD star and LD star from A transpose. So in this particular case, the focus is on A transpose. So you just find the transpose of your matrix, use the Doolittle approach, the second approach, going through Gaussian elimination to find the corresponding Doolittle upper triangular and Doolittle lower triangular. So note here, you are finding Doolittle upper triangular and Doolittle lower triangular from A transpose and not the A itself. Then you transpose this special Doolittle upper triangular to get the Crout's lower triangular. And then you transpose the lower triangular of the special Doolittle matrix to get the upper triangular of the Crout. And that is the method number 2, or the approach 2. So let's see how we can go through that to get it done. So I have my matrix A. Again, the matrix A is coming out from the system, which is 3, 5, 2, 0, 8, 2, and then 6, 2, 8. This is our matrix A. So we form A transpose out of this matrix and get it as 3, 5, 2, 0, 8, 2, 6, 2, 8. This is our transpose matrix. So as we did, the Gaussian elimination, this is equivalent to keep your pivot row. The pivot row is the row 1, which is 3, 5, 2. Then we eliminate the entry below the 3 to go to no. Transposition not done. I only repeated the system. So A transpose is 3, 5, 2, 0, 8, 2, 6, 2, 8. Sorry for that. So that is A transpose. So I keep my pivot row, and that is 3, 0, 6 is my pivot row. And so I want to make this entry 0, and that will be row 2 is equal to the new row 2 minus the new row 2 minus, what is the Gaussian factor there? 5 on 3, row 1. The Gaussian factor there is 5 on 3, row 1. And so we do that multiplication. So my row 2 is 5, 8, 2. 5 on 3 times row 1 will give us 5, 0, and then what? 5 on 3 times 6 will give us 10 there. So when I subtract, I'm going to get 0, 8, and -8. So I put that there, 0, 8, and -8. Then I go to the row 2, the new row 3 is equal to the old row 3 minus the Gaussian factor there is 2 divided by this 3. So we're going to have 2 on 3 row 1. 2 on 3 row 1. And that's where we do the subtraction. What is my row 3? My row 3 is 2, 2, 8. And 2 on 3 times row 1 will give me 2, 0, 4. And that's when I subtract, I'm going to get 0, 2, 4. So I put my 0, 2, 4 here, and that is my new system. So equivalent to, what is my pivot row now? My pivot row now is row 2. And so I'm going to have 3, 0, 6, 0, 8 minus 8. That is my pivot row. So I need to reduce row 3. And row 3 will be the old one, row 3 minus, what is my Gaussian factor at this stage, is 2 divided by 8. And that is going to give us 1 on 4. Of course, that is 2 over 8 here. And it is 1 on 4. And that is row 2. 1 on 4, row 2. So doing that calculation, let's do it over here. Our row 3 is 0, 2, 4. 1 on 4 times row 2 is going to give us 0, 2, -2. Subtract that, and you're going to have 0, 0, +6. So we have 0, 0, +6. So this ends the Gaussian elimination. And so we can write the upper triangular for this transposed matrix that but coming from Doolittle approach. So this, I'm calling it UD star. This is equal to 3, 0, 6, 0, 8, because it is this system we have, this new matrix we have here is the upper triangular. So 3, 0, 6, 0, 8, -8, 0, 0, 6. And that is this Doolittle star. And then the lower triangular of this Doolittle special is going to give us from Doolittle our diagonals 1, 1, 1, and of course the upper part 0, 0, because it is a lower triangular. And the lower part, this place, we know the Gaussian factor used over there is 5 on 3. So 5 on 3. The Gaussian factor used over here, which was when we were sending this number, this particular number to go to 0, we use the Gaussian factor 2 on 3. And finally, over here, we use 1 on 5. So this is, sorry, 1 on 4. And this is our lower triangular of the special Doolittle. So now, as you can see, if you have followed from the previous approach, then you can see that now our lower triangular of the Crout is actually the transpose of the upper triangular of this special Doolittle, which gives us 3, 0, 6, 0, 8 minus 8, and then 0, 0, 6, which is the same as the previous one that we saw. In that same vein, our upper triangular of the Crout is given by the transpose of the special Doolittle, lower triangular. And if we transpose that one, we get what? 1, 0, 0. Then 5 on 3, 1, 0. And then 2 on 3, 1 on 4, 1. And this is also the same as the previous approach. So the second approach, passing through Gaussian elimination, will lead us to the same set of lower triangular and the upper triangular. Then the rest of the procedure follows, where you solve your system Ly is equal to B for the values of y. After that, you solve Ux is equal to y for the values of x in the system, as we did under the previous approach of multiplying right side of the matrix equation and assigning corresponding terms to find the values of the entries of the lower triangular and the upper triangular. So passing through the Gaussian elimination, you will land yourself in the same lower triangular matrix and upper triangular matrix. But here you have to be very careful. You need to be very careful, as I always say, is that the matrix, you don't do the Gaussian elimination on the actual matrix, which is this one, but you do it on its transpose. And that is where you have to be very careful about. Write the transpose carefully down and go through your Gaussian elimination. And when you finish with the Gaussian elimination, remember that the upper triangular you get is not the upper triangular of the Crout, but rather a certain Doolittle upper triangular, which you will transpose to give you your lower triangular. In the same way, you write out your lower triangular matrix as if you are doing Doolittle, but call that Doolittle star because it is coming from the A transpose. And then you transpose that lower triangular to get your upper triangular for the Crout. After that, you follow through with the other methods, that other steps that you need to use to solve the system. From this discussion that we have just seen, coming from the transpose of a matrix and then transposing the answers after the Gaussian elimination to get the actual lower triangular and the upper triangular, we can make this conclusion if you are following the discussion carefully. We can make the conclusion that it is clear that if A is a symmetric matrix, if A is symmetric, if the matrix coefficient or the coefficient matrix is symmetric, then what kind of identity can we see? We can see that A transpose is equal to A. And if A transpose is equal to A, then you would agree with me that after going through the Gaussian elimination, that UD star we have is the same as the actual UD. So the UD star is the same as the actual UD. In the same way, the LD star will be the same as the actual LD, that is the Doolittle. The Doolittle star will be the same as the Doolittle itself. And then the upper triangular of the Doolittle star will be the same as the upper triangular of the original Doolittle. In the same way, the lower triangular of the Doolittle star will be the same as the lower triangular of the original Doolittle, because A and its transpose are the same. And in that case, we can say that the Crout is actually the transpose, the lower triangular of the Crout is actually the transpose of the Doolittle original. In the same way, we can say that the upper triangular of the Crout is actually the transpose of the lower triangular of the Doolittle matrix. So this is an identity that we can actually get from this Gaussian elimination approach that we have seen, that if the matrix A is symmetric, then the lower triangle of the Crout is the transpose of the Doolittle matrix. The upper triangle of the Doolittle, the original Doolittle, this time not a Doolittle star, because the Doolittle star will be equal to the original Doolittle, and that the upper triangular of the Crout will also be equal to the transpose of the lower triangular of the Doolittle method. So this is an observation or some observation that you can make from this discussion, the last stage of our discussion about the Crout decomposition passing through the Gaussian elimination method as the second approach for the Crout decomposition. And this brings us to the end of the Crout decomposition approach. And thank you very much. See you in the next video about Cholesky decomposition method. Thank you.